Welcome, Padawans, to Jedi Lesson 3. We're going to be reviewing network physical standards using Ethernet as the primary framework to explain these. This is something that applies to all network frameworks, protocols, standards, and so on. So, before we do that, what we have to do is look at the Osi model. And this is really a framework, so we have a common language to understand networking, systems, applications, all of that, and how these different functions are subdivided across all of the participating mediums throughout an enterprise, throughout a network, throughout a data center, what have you. So let's start at the beginning. The physical layer, layer 1, is what we're covering today, and that is the standard for characteristics for transmission media, for connectors, pins, cables, electrical current, light modulation, bit encoding, voltage. These are all things undefined. How do you physically build out your cables? How do you physically store data? How do you transmit data? Once you start going above this layer, layer 2 and above, that is what actually adds intelligence to all of these. Whether it's going to be voltage for networking going across a cable, whether it's going to be for magnetic media stored on a hard drive, whether when you look on the back of a DVD and those zeros and ones are encoded there, it all boils down to intelligently interpreting that information. And on the network, that starts at the data link layer. The data link layer takes these zeros and ones going down the cable and starts organizing them into intelligible information. It starts adding a unique identity and a way to forward that on a local segment. Going up the network layer, think of that as the post office. In relation to the data link, think of the data link layer as who you are. The network layer is where you are. You know, where is John right now? John is in Chicago. John is getting on a plane now and going to New York. The network layer is the location. And a good medium to think about that would be the post office. What zip code are you in at this moment? Or what GPS coordinates do you have? Continuing to go up the layer, the transport looks at what is being transported there. Again, using the post office as the paradigm, are you sending a letter? Are you sending a package? Are you sending a truck? The network traffic that's being sent similarly can be identified at this transport layer. Are you emailing someone? Are you using web traffic? Are you downloading a flash video? The last 3 layers are kind of more generalized to computer systems than specifically to the network. And at the session layer, typically this sits on your computer system, and the session layer makes the determination, is this something local to my system, sitting on my hard drive, sitting on my CD, or do I need to initiate a network call to a system and start transporting data on the network? So think of the session layer as you making the decision, do I need to mail this letter? Do I need to go to Amazon and order something, or is it something that I have in my cabinet? Is it something that I have in my garage? The presentation layer is where all of this data starts having meaning to a computer and defines file types and encryption. Is this a JPEG? Is it an MP3 audio file? Is it a video file? And last but not least, at the top, the application layer. What application is associated with this medium? Can I open up this JPEG in a web browser? Can I open it with Adobe Photoshop and start editing it? So on and so forth. So we're focusing again on layer 1. So Ethernet is something I'm pretty sure you're familiar with. If you have a desktop and you look on the back of it, this cable right here, that is Ethernet. It is a standard that was actually defined in 1984, I believe, by Bob Metcalfe. So think of it as having 2 layers of standards. The first one was what we're talking about today, the physical standards. The data link or second layer will be the subsequent video that I'll record and release. So we're looking now at the cabling, the connectors, the voltage levels. So let's first talk about the cabling. The cabling is unshielded twisted pair, and what that basically means is you're going to have 4 pairs of twisted copper wires all wrapped together in a shield, and that's basically it. It's not too terribly complex. In fact, let me kind of scroll down here so you get a better idea. The speed, the quality of the cable determines the speed of data transmission that you can attain on that cable. So category 3 is 10 megs, category 4 is 16, cat 5 or 5e is 100 meg, Cat 5e or Cat 6 is 1 gigs. So basically, the higher level of cabling, the faster transmission you can attain. Now, there is a type of cabling called shielded twisted pair, which adds an extra layer of insulation around all 4 twisted pairs of wires. The reason is you have less interference from EMI, from microwaves, from fluorescent lights. So typically this is what's going to be used in buildings just to minimize any crosstalk or EMI interference. So that's the type of cabling that you have. The connector that's used is an RJ45, and it looks like a phone jack, actually, a big phone jack, and it was based on the telco technology. Your phone actually only has 4 wires, while the RJ45 on an Ethernet has 8 wires, 4 twisted pairs. And if you look here, this kind of defines the standard. So you have 2 types, really, of how to cable this: a straight-through cable and a crossover cable. And before we go into the details, let's just think of high level. A straight-through cable is when you're transmitting from a computer to a network device. That's really the best way to think of it. If I'm going from a computer to a switch, or if I'm going from a firewall to a switch, something like that, you're going to use a straight-through cable. A crossover cable is going to be used when you have 2 devices of the same type, and that is going to be computer to computer, router to router, switch to switch. Now, just a little side note here, most devices now, most modern devices, auto-sensing, which is a feature that will automatically detect if you're connecting computer to computer or connecting router to router, and automatically make that adjustment for you. And I think since the mid-2000s, that feature has been in all network cards, all switches, all routers, firewalls, so on and so forth. So we have 4 pairs of twisted wires, but typically, in most situations, you're only using 4 out of those 8 wires. 1 and 2 is going to be used for transmitting data. 3 and 6 is for receiving data, and you kind of see a better representation right here. So to kind of standardize how these cables are going to be inserted into the connector, what sequence they're going to be in, they've developed a standard T568A, T568B. Typically speaking, T56B is what you're going to be using. Now, in reality, as long as you're consistent on both ends, when you go and crimp your cables and create them and shove them into the RJ45 connector, as long as you're the same on both sides, yes, it will work. The reason they established this standard is if you're touching a cable 2 or 3 different times by 2 or 3 different companies, 2 or 3 different people, AT&T goes, they have a cable that's connected maybe on one end to their WAN circuit, and then on the other end is going to connect to you. And that has to go through maybe a patch panel because it's going up to the 15th floor where your particular suite is. Well, you want to know that they made that cable consistently, so when you go to connect it into your network, you're not having to guess and pull the cable out, rip it apart, look and see what order it was punched down in, and then reconnect the cable, then make your cable. Now that there's a standard established, you can go based on the assumption that it's going to be set up in this particular manner. So T568B, that's typically the one used in North America. Striped orange, solid orange, striped green, then solid blue, striped blue, solid green, striped brown, solid brown. So you might say, well, why did they split the green? I have no idea. I don't know why they do this. You know, they love to make things complicated. I think my entire field is a little bit guilty of that. But I can tell you that cable manufacturers in reality have reacted to this, and because pins 1, 2, 3, and 6, which would be the orange and green, typically the coppering is a little bit thicker on those ones. The twists are more tightly compacted. You'll have more twists on the cable. So, you know, and that depends also on the cable manufacturer. But typically, since those are going to be the pins that are most actively used, those are the ones that are going to be a little bit thicker on the copper and more tight condensement of twisted instances in the twisted pair. All right, so now going down the operating mode. Think of this as how you talk between 2 endpoints, and basically it's going to be defined by speed and duplex. Speed, really easy. How fast? 10 megs, 16 megs, 100 megs, gigabit. Today, pretty much everything is going to be a minimum of 100, more than likely going to be full gigabit. Duplex is can you send or transmit at one time, or can you send and transmit simultaneously? So half duplex, you're sending or receiving. Full duplex, you're sending and receiving at the same time. So now let's start going down to the standards. So the first one we're going to start with is IEEE 802.3 10 base X network, which is 10 megabits per second, old version that came out in the 80s. The original two versions, 10 base 5, 10 base 2, thin-net and thick-net, and that used coax cable. And let me tell you, not fun to work with. This guy was, in the thick net was this half an inch around, thick as your thumb. Trying to bend that around corners, absolute nightmare. Maximum segment length, 500 meters for coax cable, 185 meters for thin net. Now, one thing I want to point out to you, if you remember from the previous video, the physical topology for this is a bus. That means a single break in the network will bring everyone and everything down. Why? Again, the reason is there's no resistors there to catch the signal as it's going back and forth between two endpoints, so it's going to bounce around and corrupt the signal. So, this was really a limited attempt. This was the initial attempt at a networking standard. As it kind of evolved, this is the reason they switched to the category cabling, the Cat 3 through Cat 5 and 5E and 6. Number one, it's a lot easier to work with. The twisted pair is much more flexible, much more pliable. It's also what had been used by the telco industry for many years. Its maximum segment length is 100 meters, so that's still adequate. But the biggest benefit that you're getting is this is now built in by hubs and switch, a star topology, which means a break in a cable is only going to affect that particular segment. It is not going to bring down the entire network as a whole. So this is the initial standard here. IEEE, by the way, this is an organization that defines many standards. They defined wireless, for instance. They define many things. You can Google them on the internet if you want and get more information on them. So building upon that, we came out with the 802.3 U 100 base X, which is fast Ethernet, and as it implies, the 100 here is really depicting the speed. If you go down here, 10 base, this is the speed, 10 megabits per second. Here they've dramatically increased the speed to 100, more than 10 times. So this was a significant jump in the early 90s. They have a couple different types here. So the standard one that you'll see, the most common one is this 100 base TX, and it uses category 5 cable, uses, just as you saw before, pins 1, 2, 3, and 6, so it's only using 2 of the 4 twisted pairs. Like 10 base T, it's 100 meters max, and it uses the hub switch topology. They realized, though, when this came out, here's the problem, and let me preface this before going into the details of 100 base T4. Pretend now you're a building owner. You work for a real estate company, and you have cabled the entire 20 or so stories with Cat 3 cabling for 10 base T. And again, let me go up here, just in case you didn't get it. It might behoove you to take some screenshots or whatnot, or take notes. Cat 3 for 10 megs. So you went through and cabled your entire building with Cat 3. So that means you're limited to 10 megabits per second. Now this new technology comes out. Can you imagine the cost? And you imagine the downtime and how you would have to respond to your clients to rip all of that Cat 3 cabling out and replace it with Cat 5. I mean, the effort would be massive. Hugely invasive to your customers, hugely expensive. So an intermediary solution was 100 base T4, and what that does is use all 8 pins of Cat 3 cabling and pushes through 100 megs over that cabling. Other than that, it's the same as 100 base TX. It's 100 meters length. It's supports a star topology through hubs and switches. One thing that you should realize, though, it does not support full duplex operation. It is half duplex only. So it uses all 4 twisted pairs, all 8 pins, to send or to receive simultaneously. Due to distance limitations, they have initially built this out into fiber. So 100 base FX is actually the fiber version of this. There's many different flavors. There's, first of all, are you using multi-mode or single mode? Multi-mode is actually just an LED, whereas single mode is a true laser. In general, multi-mode is going to give you much greater distance, or much shorter distances than single mode. Because single mode is a true laser, you can see here you can get up to 10 kilometers, even more. I've even seen particular specs and implementations that can go 100 or more kilometers. So realistically speaking, multi-mode is going to be for something probably within the same building. If you're going within a metropolitan area, several blocks away between buildings, you're going to be using single mode. There's a couple different connector types. The most popular one, ST, SC, LC. I actually got kind of a screenshot from the web. You can see this is the ST connector, which looks like the BNC or kind of coax connectors. SC, LC, they look kind of similar. The only difference would probably be the size. SC is actually a little bit larger than LC. LC is kind of smaller, and typically you have them in pairs. Again, just as with Ethernet, you have transmit and receive. Same thing with fiber. The difference is there is really no auto sensing. With fiber, one cable is definitely dedicated to transmitting, the other is definitely dedicated to receiving. And on the other end of the connection, the opposite is true. Data is going one way on one cable and the other way on the other side. There's other problems that could lead to with if you have unidirectional communication. There's other detection mechanisms built into the hardware to find and notify that and to try to correct. But typically speaking, one cable's communicating one way, the other cable's communicating the other way. All right. More modern is Gigabit Ethernet, and at this time, because of the fiber, they actually broke out the standards into two main categories: electrical or copper Gigabit Ethernet, and then optical Gigabit Ethernet. So starting with the copper, 1000 base CX was one of the first flavors of copper out on the market. It was kind of really like a beta release, if you think of it that way. It used a shield twisted pair. It used a slightly different connector, 8P, 8C. It looks very similar to the RJ45, very subtle differences, but you had to get these specific connectors to make it work. It had a very short range, only 25 meters. Typically, when this was released, you were only using this to connect your core devices, maybe your fastest servers, or maybe just the uplink for all of your child devices to the main core network. That's typically what this was used for when it was initially released. Eventually they got Gigabit running on even Category 3. Now theoretically you can run it on Cat 3 cable. Don't recommend it. It's not rated for that kind of electrical signal. You will have problems with interference and crosstalk. It does use all 8 pins in the twisted pair, has a limit of 100 meters. Going through optical, they divided again between long wavelength laser and short wavelength laser. The width of the actual fiber wire is very small, 62.5 or 50 micron core. That is thinner than a human hair. And to do that, it's actually created in liquid form, and they will surround it with a Kevlar coating. Kevlar is the same thing that's used to make bulletproof vests. Again, uses the same type of connectors. Depending on if you're in multi-mode or single mode, you're going to get different distances, and depending on if you're long wavelength or short wavelength, that will also determine your distance. Typically, if you're creating like a server room, you're going to be using short wavelength, and you're probably going to be using multi-mode. Single mode is when you need longer distances. Long wavelength is definitely going to be used when you have a large, say, college campus or connecting multiple buildings. The last thing that I want to talk about is the voltage standards. This is basically telling you how those voltages are to be put on the wire to have them mean something. So the initial one that I want to go over in probably the most detail is Manchester encoding. It was the first one really used in 10 megabit transmission, and there's a common misconception out there that is the voltage high or low. That's not quite accurate. It's really the voltage transitory state within a cycle, within a period. If it is going from high to low or going from low to high, that determines if it's a 0 or a 1. So the specifics here, each bit is transmitted in a fixed unit of time called the cycle or the period. A value of 0 is expressed by a low to high transition. A value of 1 is expressed from a high to low transition. And by the way, I did put this note here. General Electric That convention is true for Ethernet. Ironically, it's actually reversed. Again, don't know why. I'm sure there's a historical reason. If I Googled it, I'd find it. But just be aware. For comprehension's sake, I'm using the General Electric model to explain it, but it is reversed in Ethernet. Another thing here is the midpoint of the cycle or period is actually what determines that. So kind of using this example that you have here, this is a cycle, this is a cycle. These dotted lines here represent cycles. And where you're going to in between, in the middle state of that cycle, is what determines if it's a 1 or 0. So you can see you're going from 0 to 1, that's a 1. You immediately drop down to, at the start state, to not signify data, back to 0, go to 1. Since you're going to be going to a 0 here, you stay at your current position and drop down. That transition is a 0. So it might seem a little confusing at first, but just realize it is really where you're going, not where you are at, that determines a 0 or a 1. So eventually, it was kind of limited the way it goes. They improved upon that. They made 4B, 5B encoding, which was used in 100 meg transmission, and the biggest improvement is you had a predefined library. So it takes groups of 4 bits, maps them onto 5 bits, and these create words. And the most common ones I included here is the start and the end of the transmission, the error state, and the idle state. The idle state means no data is being transmitted at the moment. It's just kind of doing a keep alive. Yes, there is signal on the wire, but no data is actually traversing. And there's certain rules. You can have no more than 3 consecutive 0 bits because you have a defined dictionary, a library of functions or whatnot. That actually isn't a problem. So you can see here you have 3 zeros, that's it. No more than 3 consecutive zeros in the library. There was an improvement made, 8B, 10B for gigabit fiber networks based on the same thing. The logic is fairly similar. The last one I want to talk about is PAM5 encoding, again used in 1 gigabit copper, pulse amplitude modulation. So message information encoded in the amplitude. So we're no longer talking about voltage states between 0 and 1. You now have significantly more levels. You actually have a total of 5 levels. So you can use these to represent 2 bits simultaneously and then the last bit for error correction. Much more efficient. But without going into too much detail, each one can be 250 megabits of throughput. Obviously, tremendous more data through this encoding mechanism than ever dreamed of with this original Manchester coding. If you want to learn any more about these, you can Google it, get super nerdy. I want to give you an overview because a lot of this isn't covered in the series. A lot of it is kind of just glossed over and only the standards of cabling and connectors is covered. I want to give you a little bit deeper picture to that, at least give you an idea of what to Google. So I think that is it for now, covering the physical standards of Ethernet. There are other standards out there. They may be covered in future videos. For instance, wireless, 802.11 wireless, whereas Ethernet is 802.3, wireless is 802.11. It follows similar convention at layer 2, but layer 1, based on radio frequency, is vastly different mechanism. So this is the Cisco Jedi signing off.